Hey y'all! Welcome to West Texas 3D Printing, tutorials curated by nerds, delivered by your favorite avatar, Lulu. Weak prints usually don't fail because of the filament. They fail because of poor layer bonding, bad orientation, insufficient walls, or incorrect slicer settings. Strength is controlled far more by geometry and print settings than by material alone. Let's go through the major factors that determine part strength and how to improve each one. First, orientation. Layer lines are the weakest part of any 3D print. If a part is pulled perpendicular to the layers, it can snap easily. If the force runs parallel to the layers, strength increases dramatically. Rotate the model so layers align with the primary direction of stress. For brackets, hooks, handles, and mechanical parts, orientation is the single most important strength factor. Next, wall count and wall thickness. Walls carry most of the load in a printed part. Increase wall count to 3 or 4 walls for functional pieces. Slightly increasing wall line width also improves bonding. A thicker wall almost always adds more strength than increasing infill. Now infill pattern and percentage. Infill adds internal rigidity, but it's not the primary strength source. Use structural patterns like gyroid, grid, or cubic. Increase infill density to about 25 to 40% for strong parts. Avoid lightweight infill for load-bearing designs. Next, layer height. Smaller layer heights improve layer bonding. For functional parts, use 0.15 to 0.2 millimeter layers. Thick layers reduce contact area between layers and can weaken bonding, especially with PLA. Now print temperature. Temperature directly affects layer adhesion. If temperature is too low, layers don't fuse properly. Increase nozzle temperature by 5 to 10 degrees for stronger bonding, and always print with dry filament for consistent extrusion. Next, cooling. Too much cooling makes parts brittle. Reduce fan speed when printing strength-critical parts. For PLA, aim for about 40 to 60% cooling instead of full fan. For PETG, use minimal cooling. Now print speed. Faster prints reduce bonding time between layers, slow down outer walls, and reduce overall speed for structural parts. Speeds around 20 to 40 millimeters per second usually produce better mechanical strength. Next, line width. Increasing line width improves strength because each extrusion line contains more material and bonds better. Set line width to about 115 to 120% of nozzle size. For a 0.4 millimeter nozzle, use roughly 0.46 to 0.48 millimeters. Now bed and chamber temperature. For ABS, ASA, and nylon, warm environments greatly improve bonding and reduce cracking. Use an enclosure, avoid drafts, and maintain stable temperatures throughout the print. Next, material choice. PLA is easy to print but brittle. PETG is stronger and more flexible. ABS and ASA handle heat and mechanical stress better. Nylon and nylon composites offer the highest strength and impact resistance. Choose material based on how the part will actually be used. Now internal geometry. Sharp 90-degree internal corners concentrate stress and promote cracking. Adding fillets or chamfers spreads stress and dramatically improves durability. Next, internal bridging. Sagging bridges inside parts weaken the bond between infill and walls. If internal bridges exist, slow bridge speed and increase bridge flow. Now wall to infill bonding. Increase infill overlap percentage, so infill bonds tightly to the walls. This reduces internal separation and increases rigidity. Now a quick strength checklist. Correct orientation. 3 or more walls. Increased line width. 25 to 40% infill. Reduced cooling. Higher temperature for better bonding. Slower print speeds, dry filament, rounded corners instead of sharp ones, and material appropriate for the job. When these factors are balanced, printed parts become dramatically stronger and far more reliable. Thanks for watching from all of us at West Texas 3D Printing. Yes, even me, Lulu. Like, subscribe, and keep turning chaos into clarity.